A projectile is a particle or body that is subjected only to the force of gravity, and thus the constant downward acceleration due to gravity as it moves along a path in space. Although the projectile is also affected by air resistance, the effects of air resistance are often neglected in problems involving projectile motion. Because there is no force and thus no acceleration in the horizontal direction, the projectile maintains constant horizontal velocity. However, because gravitational force and gravitational acceleration act in the vertical direction, downward toward the center of the Earth, the projectile undergoes changes in the vertical component of its velocity. It is convenient to analyze the free flight motion of a projectile in terms of its rectangular or x-y components. Consider a projectile launched at an initial position x0, y0 with initial velocity v0 that has components v0 x and v0 y. Okay, so taking a look at this diagram, here's our projectile that has initial position x0, y0, and has some initial velocity v0, this vector here in this two-dimensional space, with an x component v0 x and a y component v0 y. During its motion, the projectile experiences constant downward acceleration due to gravity, where a sub c, the constant downward acceleration, which we denote as g, that equals 9.81 meter per second squared or 32.2 foot per second squared, assuming we are on the surface of the Earth. So the blue curve represents the path of the particle's motion, this projectile. So at some final or later time, it has a different velocity, okay, this velocity vector v, with an x component vx and a y component vy. And it also has changed its position such that its coordinates now would be in general x and y. So we can analyze the horizontal motion of the projectile separately from the vertical motion, since the acceleration due to gravity only acts vertically. Regarding horizontal motion in particular, since a sub x equals 0, there's no acceleration in the x or horizontal direction, we can apply the kinematic equations for constant acceleration to obtain the following. Okay, these three shown first would be the equations we learned earlier in chapter 12. These three over here would be applying it to this specific scenario of projectile motion, where a sub c in this case equals a sub x equals 0 for the horizontal motion. Therefore, the first equation gives us v sub x equals v naught x, meaning the x component of its velocity never changes, x or x final equals x naught plus v naught xt, and v sub x equals v naught x. Okay, the first and third obviously give us the same information, so that equation doesn't give us anything new. So there's really just two useful equations here for motion in the horizontal direction. Regarding vertical motion, now we have some non-zero acceleration, the acceleration due to gravity. Since a sub y equals negative g, because it acts downward in the negative y direction, we can apply the kinematic equations for constant acceleration for the vertical component of its motion to obtain the following. So the first equation gives us this: vy, or v final y, equals v naught y minus gt. Y, or y final, equals y naught plus v naught yt minus 1/2 gt squared. And vy squared, or v final y squared, equals v naught y squared minus 2g y, or y final, minus y naught. So three very useful equations for vertical motion. When solving problems that involve projectile motion, such as this problem shown here, it is necessary to first establish an xy coordinate system showing the x and y axes and clearly showing where the origin is. It is helpful to summarize the given data, write out all of the kinematic equations previously mentioned for projectile motion, then study the equations and the given parameters to determine which equations may be most useful in calculating the unknown values for that particular scenario.